All right, welcome all. So the short summary of yesterday was that we can rewrite the maximum a posteriori optimization problem in a discrete pairwise Markov random field as an integer linear program. And today I want to show how such an integer linear program can actually be solved. So let's look at the structure of the ILP. It comes under other names. It is also called, the particular type that we're looking at is also called a 0-1 linear program, because we don't have just an integrality constraint, we even have the constraint that these variables that we introduce have to take values either 0 or 1, or it's also called a binary integer program. Now, we were saying that we try to maximize some function which is linear in our variables of interest. Yesterday I wrote mu, today I'm writing x in keeping with the standard notation of this field. And as written here, this would be a linear program which is convex. But if we impose in addition that x should be, each element of x should either be 0 or 1, then this is an integer linear program which is non-convex. So let's look at what this means geometrically speaking. We have a matrix, this matrix A here, and I can consider the rows of A. So the first row, I will call it A1 transpose, and so on, up to A M transpose. And if we look at this set of points x that fulfill our conditions, then I can also write this as a series of conditions. So I can say it's the set of points x for which this holds for every I. Okay, now what we have written here is an equation for a half space. I can say that AI transpose x minus bi is less than or equal to 0. If I did write that this should be 0, this would be the Euler form of a plane. So I'm taking a two-dimensional example here for illustration. And please try and copy this example exactly. So I'm showing integer coordinates here. And for example, I could have the condition that condition for my first plane to look something like this. So this would be, let's say, the condition that A1 transpose X minus B1 equals 0. And if I'm now asking that the values be less than, so now I have to still point out in which direction is A pointing. If I'm now asking that it should be less than or equal to 0, now I need to think in which way round this has to point. This way around. Then this defines a half space, a feasible half space. So everything to the left of this line is permissible. Now I will add a second condition. Saying that A2 transpose X minus B2 should be no more than 0. And this again defines a feasible half space, namely everything to the right of this line. So everything in the direction of the arrow which I've drawn is feasible. And let me add just a third constraint, which is simply going to be this, that A3 transpose X minus B3 should be no more than 0. So, in other words, I now get a feasible region that I'm coloring here in yellow. All right, so if we generalize this, then we can say that the set of half planes which we're defining here, taken together, defines a polyhedron, or the empty set. It can also occur that the conditions are mutually exclusive and I have no feasible solutions whatsoever. Yeah? But otherwise, I get a polyhedron, so a convex body which has planes as its faces. Now, if we remember where or what part of the ILP defines this polyhedron, it was this part here. So those constraints give me the polyhedron. And let's remind us, where in the graphical model did this come from? I will look at yesterday's derivation. This was some statement about the mu's, and the mu's were indicator vectors. So actually, this part came from the structure of the graphical model itself. Okay, so the blue part here is governed by the structure of our graphical model. Where by structure I mean what sets of random variables do we have and what others are they connected to. Now, in addition, we have this ugly integrality constraint, and by the way, you see that the picture that I've drawn at the bottom, it was not a true 0-1 linear program because, well, if it was, then these constraints would tell me that the points shown here in red are the ones that fulfill this constraint of being binary. All other integral points which I had previously marked in black, they're still integer, but they're larger than the ones, than the values I wanted. Okay, so this was the red part of the equation. And now we're still missing the direction in which we want to go. Yeah, so this part here. Do you remember where in the graphical model this came from? Yeah.
Do you want the most probable solution or the minimal energy solution?
Yeah. So if you look at the derivation from yesterday, the variables were called mu. Today I've called the mu as x. Yeah. And now the potentials, psi, what we called psi yesterday, those are the terms that tell us what is actually a favorable and what is an unfavorable value for mu. Okay. So the green part here, this actually came from the potentials of our graphical model. And so let's say we look at the stereo problem, we can set our graphical model. Where does the data actually enter? After all, you know, we have camera pictures. Where does the data enter? In this optimization problem?
So also through the potentials, the data influences the potential.
Exactly. We had two kinds of potentials. The data enters through the potentials. We had two kinds of potentials. We had the unary potentials that coupled our local estimate to the data that we locally observe. And this was written in yesterday's notation. Let me move this here. In yesterday's notation, the unary potentials were those. And then we had the pairwise potentials that are meant to encourage smoothness. Yeah? So for example, if we now change the observed data, this will change our unary potentials, so it will change the vector C. Or if we change, let's say, the strength of the smoothness prior that we want to impose, this will also change the value C. Okay. Now, so far in this picture here, I only defined what is the feasible region. I did not point out. So if we take only the LP constraints, then the yellow area is the feasible region. If I intersect this with the constraints that we want a binary solution, then actually I only have three admissible values, this, this, and this. So those would be the allowed configurations. But so those are allowed, but now we want a statement. Now we want a statement about which of these is actually preferred. Yeah? And this comes from the objective function, where I have some cost vector. So let's say, for example, that the cost vector points, let me think, let's say that the vector C points in this direction, then I forget if yesterday we wrote maximization or minimization. Today I wrote maximization. Then I can write, I can draw equicontour lines. I could have drawn this vector C anywhere, yeah, but I already planted its root at the linear programming solution, and this vector here now induces equicost contours. So I'm I'm showing here, excuse me, I'm showing here in green the gain that can be achieved. So let's say, this would be a gain of C or of some, well, actually, probably I should plant my vector C at the origin. Yeah? So I'm putting C here, but the direction remains the same. So all these equicontour lines are orthogonal, and then you can see that here I have a gain of 0, here I have a gain of 1, a gain of 2, a gain of 3, and so on. Okay, so those were the equicontour lines that I've just shown of my cost vector. Which was pointing in this direction roughly. I think I had it point in this direction. And now let's try and, for starters, solve the linear programming problem only. Yeah? So I'm looking for the most extreme point of my yellow polyhedron when projected onto this reward vector C. And the most extreme point will actually be this one here. So in other words, this is going to be the solution of the linear programming part of my optimization problem for this given set of constraints and for this given cost vector. Now, a typical way to solve the integer linear programming problem is to say that we want to start by solving the LP, and then we impose the integrality constraints afterwards. And now the question is, how can we, if we've already ended up at this point here at the solution of the LP, the question is, how can we get to an integral solution? One common heuristic is to simply round. So, for example, if I want to impose integrality constraints, not necessarily 0-1 constraints, then if I'm rounding, the closest solutions would be probably this is the closest integral solution. So I could round to this solution, or I'm not sure where exactly this corner of my yellow triangle lies. Maybe the closest solution is that one, but either of these solutions is not feasible because it lies outside the allowed polyhedron. Now, in addition, I did not just want integral solutions. I actually wanted solutions that were 0 or 1. Yeah, so I wanted the only feasible solutions are either this one or that one or that one. And now, by the way I drew the cost vector, I think the closest ILP solution is probably this one here for the green vector. Solution of the ILP. And what I did was that or am I wrong? Let's see. What's the slope between these two? This is a slope of +1. And my vector, so this angle here, alpha, is, this vector alpha in my picture is a little bit smaller than 90 degrees. And hence the solution on the right is indeed more favorable. Yeah? So this is the solution of the ILP. Okay. Now let's look graphically at a few cases. For example, let's take a pink cost vector pointing in this direction here, then the solution of the LP would now be this one here. That would be the solution of the LP, because because this is now the corner of my yellow region, which lies furthest along this vector. But in between I can find some tricky solutions. Let's be tricky now. So I'm now taking the right angle here, and I'm taking the right angle there. Can you tell me the LP and the ILP solution for any vector within this region that I've just shown? So I'm using another color, let's say this purple here. Any cost vector lying in this area or in this part of space, what would be its LP and what would be its ILP solution? So again, how did I construct this region? I used this red line, which should have a 90-degree angle with regard to my two integral solutions that are lying here, and I used the blue region, or the blue area, which has a 90-degree angle to this one constraining half plane. Yes?
So your LP is still the apex of the triangle, but your ILP is the origin?
Exactly. So for this funny color here, the solution of the LP would be here, but the solution of the ILP would be down there. And well, I have handcrafted this example to show that actually the ILP solution can be very far away from the LP solution. Because you see, if this is our LP solution up here, you know, you would usually think that, well, the closest binary solution would be that one, or at least if I use Euclidean distance, this is true. But if I now use, instead of Euclidean distance, this metric induced by my cost vector, then actually the origin in this case is the best solution. Yeah? So let's collect these comments here. First, for the linear programming part, at least one optimal solution always lies at a vertex of the LP polyhedron. So I'm now referring to the case where, you know, I'm looking at the yellow region, and whichever cost vector I am picking, a valid solution which maximizes my reward will always lie at exactly a corner. I've written at least one optimal solution because I can construct special cost vectors. Let's say if I'm using this reward vector here, then any point on this boundary of my polyhedron is equally good, including the vertices. So in this case, all these solutions are equally good, but they're not unique. So I have some degeneracy in my optimization problem. But even when I do have degeneracy, there is one solution, at least given by a corner, which is no worse than the other degenerate solutions. And for normal cost vectors which do not induce degenerate solutions, then it's always one of the corners which will give me the optimum. Everybody happy with this statement? Okay. This can be proven more formally, but I think the intuition is clear. Next, the ILP solution can be far from the LP solution. And normal rounding is often a poor heuristic. Poor either in the sense that the solution that I will get out is not feasible at all, or that it is feasible but suboptimal. And this example that I gave here, it may look a little handcrafted in 2 dimensions, but actually in higher dimensional problems, this is quite a frequent occurrence. And then again, in relation to the graphical model, so the feasible region is dictated by the structure of the graphical model, but the cost or reward is given by the choice of potentials. And the data that we observe is also a part of these potentials. And generally speaking, solving an LP, so a convex problem, is easy. And solving an ILP, or a non-convex problem, this can be extremely hard. Yeah?
This might be a little bit constructed, but what happens if I have very few constraints? Then we might get the case that we don't have a closed surface, but maybe it's open on one side.
Yes.
Then we could have no LP solution, because this
Yep.
would lie in infinity, but still, ILP solutions would exist, because we are bounded by some integrality constraints.
Well, we have to distinguish. So the question was, can we also have open polytopes? Yes, we can. And then the optimization problem is ill-defined, because we will get out solutions that would like to be infinite. And this is still true if we impose the integrality constraint. The integrality only would say we want a whole number of, we want the infinite number to be integer rather than real. Yeah? If we impose this constraint that we only want 0 or 1 values, then yes, we get a finite set of elements to choose from, which, however, in many interesting problems is very hard. So let's now talk about how can we solve this ILP. How to solve an ILP. Perhaps your first idea, or my first idea, is to enumerate exhaustively. This is usually a bad idea. So let's take the grab cut example. Let's say we have two possible states, foreground or background for every pixel. And let's say we have a megapixel image. So we have 2 to the power of 10 to the 6 possible states to try out. You don't want to do that exhaustively. Okay. This is so the number of particles in the universe is 10 to the 81 or so. And you know, if I convert the 2 to the power of to 10 to the power of, this probably means I only have 10 to the power of 999,999 rather than 10 to the power of 1 million. It doesn't really help. No? So complete enumeration, no, we don't want to do. An approach that is quite popular is to use branch and cut, and this is what I want to look at with you now. Branch and cut, or branch and bound. And let's look at this again graphically. I will try and copy this and clean it up a little. So we get rid of all the unnecessary stuff. You can also just redraw the thing, probably easier. Okay. So branch and cut does the following. We first solve the LP part of our problem. And we get for a reward vector pointing, let's not be too tricky this time, so we simply let the reward vector point in this direction. Yes? Oh yes, should we align the points to the grid? That's a very good idea. Thank you. Okay. So this is our reward vector, let's say. And the solution of my LP is going to be here. And this happens to be fractional. So this is maybe, I'm now guessing these numbers. This is perhaps 0.6, and the y coordinate is 1, 2, and perhaps 2.54 or something. Okay, these are now the x-y coordinates of the solution of the LP. And I can now say, but I know that I want an integral solution out. So I can introduce new constraints to obtain 2 linear programs to solve. The first linear program will add this constraint and say we're only looking at either the right-hand side of this, or we're looking at the left-hand side of that. So we had an original LP, and now we create two new linear programs. One linear program imposes, in addition, the constraint that x1 must be no less than 1, and the other one imposes that x1 must be no more than 0. And I now get out two new linear programs this one here and this one. So I now have two new linear programs with additional constraints, and I can solve them again, and then I will find, for example, for the turquoise, is it turquoise? I will find my new solution of the LP, which this time is going to be 1.0. So it's already integral in the x direction, but not yet in the y direction. And in the other direction, it is perhaps, I don't know, 1.5 or something. And I also get a solution of the other LP with coordinates 0. So again, this is integral, and perhaps 0.7. Now, let's, which of the two should we first explore? Remember that I can compute a reward for either of these, and the reward of the turquoise solution is going to be higher than the reward of the purple solution. Okay, so I'm going to first branch on the turquoise solution. So now I'm going to branch in the other direction. I'm going to say that I'm adding a new constraint which says either I should have a value of x of x2 which is no less than 2, or I should have a value of x2 which is no more than 1. And well, if I intersect the new constraint with the turquoise region, I get out the empty set. I have no feasible solution at all. But in the other case, I now get, okay, I'm now tilting my reward vector a little bit to make the thing more clear. Yeah, let's argue that the reward points here. At this point, I get an integral solution. Yeah, I get a new solution. I get a solution to my LP, which lies in this corner here. Let me pick a new color. Okay, this is my new feasible region, which I painted in brown. And the solution here, this is the solution of the LP, which is now 1.0, 1.0. So this is integral. And I can compute its reward. and the reward vector was pointing in this direction here. And I can now compare the reward of this integer solution with the reward for my purple region. And at this point, I will find that the solution of my brown region, which is already integer, gives me a higher reward than the solution of my purple region, which is still fractional. Okay, so the solution of the brown LP already is integer and gives a higher reward than the solution of my purple LP, which is still fractional. Which is partly fractional. Now, we can argue, if I now impose additional constraints on the LP of the purple region, can its reward become any higher? No, because
It's just an additional constraint.
yeah, I will only impose additional constraints. They cannot increase the reward. They can only make the feasible region smaller, so they can only make the solution less attractive. Yeah. So if I have a solution which already is integer and which is better than the best solution I can possibly hope for in this other branch, then I can terminate my search and I am done. Okay, so I can terminate my search because I have exhausted my search tree. Yeah? So one branch of the search tree was the empty set. There was no solution at all. One solution was integral and already better than any of the fractional solutions. There is just one fractional solution that I have an alternative. So in other words, I don't need to explore this entire tree of possibilities. So this is this algorithm that I've just described in terms of an example is called branch and bound. And this branch and bound algorithm does afford globally optimal solutions. It does afford globally optimal solutions, but there is no guarantee that my search, that I will be able to terminate my search early on. Yeah, so it does afford globally optimal solutions, but the worst case is still a complete enumeration. Because, you know, if I had chosen a different cost vector, if I had chosen my tricky cost vector from above, yeah, you remember the one which was lying in this special region here on the left. If I had chosen this tricky cost vector, then I would have had to exhaust my tree completely. And you know, here this is an innocent example with just two variables and you know, very few constraints. Now imagine if you have millions of variables and so on. Yeah, so this is why solving linear programs quickly is so important, because we need to do it many times in such a search tree. And this is also why, in the worst case, you know, things will take longer than your lifetime, etc. Yeah? So this is why interlinear programs are hard indeed. Okay, any questions? So yesterday we saw how the map problem in a graphical model can be translated to an ILP. Now we've seen how we can solve such an ILP if we have an oracle that somehow gives us the solution of an LP. And after the break, we will look at this oracle. So we will look at this crucial ingredient of how do we actually solve a linear program. And we continue in 10 minutes.